Okay, today we're going to talk about the chain rule. For our do now, we're asked to find the derivative of the quantity 2x plus 1 squared. There are two ways we could go about doing this. One way, we could square it out, and we would get 4x squared, right? You get the first term squared, plus twice the product, plus the last term squared. So we could first square it out and then find the derivative. And we would get 8x plus 4. Not bad. Another way we could find the derivative is to write this as a product. 2x plus 1 times 2x plus 1, and use the product rule. So we would get first 2x plus 1 times derivative of the second times 2 plus the second 2x plus 1 times derivative of the first. These are like terms. We can combine them. We have 2 of these plus another 2 of those, so we get 4 times the quantity 2x plus 1, which equals 8x plus 4. We have the same answer. But then we start to wonder, well, it was a little bit of work. Could we have just used the power rule? So in other words, we had this function, y equals the quantity 2x plus 1 squared. What if we had just gone ahead to find the derivative by using the power rule? Just ignore the inside. We have something squared. When we take the derivative, we get 2 of it to the first. So we just ignore the inside function. The only problem is this is only 4x plus 2. It's not quite right. Think about what we would have to multiply it by to get the real derivative. We're off by a factor of 2. We would have to multiply this by 2. If we did that, we would have the right derivative. But how are we supposed to know what to multiply by? Where did this 2 come from? Well, when we use that power rule to find the derivative, we just ignore the inside function. And the 2 is the derivative of the inside function. So we can just take the derivative of the outside function, 2 times the quantity 2x plus 1 to the first, as long as we remember to multiply by the derivative of the inside function. This is what's known as the chain rule, and we will be using this to find the derivative of a composition of functions. What the chain rule says is that whenever you want to take the derivative of a composition of functions, you may remember, some people like to say fog and goff. If you have f of x equals x squared, and you have g of x equals 3x plus 1, the composition f following g of x can be written as f of g of x. And this is a composition of functions, and it means take g of x, which is 3x plus 1, and plug it into your function f. This would give you 3x plus 1 squared. This is a composition of functions. It's an example. So instead of just taking a function of x, you actually plug another function into another function. So you plug one function into another. And this is what we're going to use the chain rule to differentiate. what the chain rule says is that when you want to take the derivative of, if you ever get the derivative of f of g of x, you have to take the derivative of the outer function. So the outer function is f. So f prime evaluated at the inside function. We leave that inside function g of x alone. So f prime of g of x times the derivative of the inside function. The inside function is g of x. So the derivative would be g prime of x. I'm going to have it here in words. The derivative of a composition is the derivative of the outer function evaluated at the inside function times the derivative of the inside function, the inner function. Now, in order to be successful with the chain rule, you have to be real clear what the outer function is and what the inner function is. So before we get to some examples, I just want to give you two suggestions. And the first is, whenever you see any trig function to a power of x, let's say you have sine cubed x, think about what's being cubed and rewrite it with parentheses. Sine cubed x is just a short way of saying the cube of sine x. We're not cubing sin. We're not cubing sine. That's impossible just to cube a function without an argument. We're cubing the sine of x. Now, this makes it real clear that the outer function is the cubing function and the inside function is the sine function. Another little suggestion I have for you is if you have a trig function with an angle, unless that angle is just x, put parentheses around the angle. So if you have tan of x squared, you see two functions. You see the squaring function and the tan function. Well, once you put parentheses around the angle, now you can see that the outside function is the tan function and the inside function is the squaring function. Now we're ready to start. Example A. We have y equals the cosine of x cubed minus x. This is a composition of functions. It's not just the cosine of x, it's the cosine of another function of x. So to take the derivative, you have to take the derivative of the outer function. The derivative of cosine of an angle is negative sine of the angle. The angle never changes, right? The derivative of cosine x is negative sine x. So the derivative of cosine x cubed minus x, you start out by writing negative sine x cubed minus x. So we just took the derivative of the outermost layer, the cosine. But now we have to multiply by the derivative of the inside function. The inside function is x cubed minus x. So we have to multiply by its derivative. The derivative of x cubed minus x would be 3x squared minus 1. And that's it. So the derivative of the outer function evaluated at the inside function times the derivative of the inner function. Okay, example B. We're asked to find the derivative of secant to the fifth of 3x. Before we differentiate, we need to rewrite this using our parentheses. We need a parentheses around the angle, 3x. And we have that fifth power. Right? What's being raised to the fifth power is the secant of the angle. So you need one parenthesis. You need to open the parentheses in front of secant and close it after the angle. That's what's being raised to the fifth. Now we're ready to apply the chain rule. Differentiate using the chain rule. You take the derivative of one layer at a time, starting with the outermost function. You peel away. It's like peeling an onion one layer at a time. And when you take the derivative of a layer, leave its inside function alone. So the outermost function is the fifth power. So we're going to take the derivative of that first. To differentiate something to the fifth, to bring down the 5, we're going to use the power rule. We're going to leave the inside alone, and the new exponent will be 4, 1 less. So the derivative of the outermost function is 5 secant of 3x, and we're going to leave the inside alone, to the 4th. So we took care of the outermost function. We differentiated it. The next layer, we're working outside in, is the secant. To take the derivative of the secant of an angle, it's secant of the angle, tan of the angle. So it's secant of 3x times tan of 3x. That is the derivative of the secant. Now we need to multiply that by the derivative of the innermost function, 3x, which is just 3. So there's the derivative, and we can clean it up by putting the coefficient outside, 5 times 3, and up front we have 15. Secant of 3x to the 4th times secant of 3x to the 1st. We can write that as secant of 3x to the 5th. Right, you add exponents when you multiply, right? This is to the 1st, you add exponents. And then we have the tan of 3x. Example B. Now C looks intimidating until you rewrite it with fractional exponents in parentheses. The fifth root is the 1/5 power. So we can rewrite this as 2 root of x squared is just x to the 2/3 minus 4x. So rewriting our function first, so now it's clear what the outermost function is. It's a composition. We're going to apply the chain rule to get the derivative. The outermost function is the 1/5 power. To take the derivative of something to the 5th, we bring down the 1/5. We leave the inside alone, and we subtract 1. 1/5 minus 1. 1/5 minus 5/5 is negative 4/5. Evaluate at the inside. So we took the derivative of the outermost function, right? Now, inside, we have a difference. We have x to the 2/3 minus 4x. So to take the derivative of that inside function, we just take the derivative separately and subtract. The derivative of x to the 2/3 is 2/3 x to the negative 1/3 minus the derivative of the 4x would be 4. And there we go. We're going to leave it as is. So derivative of the outside, evaluate at the inner function, times the derivative of the inner function. D, we have a little rewriting to do. We don't want to leave it tan cubed x inside, so we're going to rewrite this as x plus the tan of x cubed all raised to the 4th. Just changing that tan cubed x to parentheses around the tan x cubed. Now we're ready to differentiate. The outermost function is the 4th power. So we start out with the power rule. 4, we're going to leave the inside alone, and it'll be cubed. So x plus tan of x cubed, or tan cubed x, same. We've now taken the derivative of the outermost function. Now we look inside, and the inside is a sum. We have x plus the tan of x cubed. To take the derivative of a sum, you take the sum of the derivatives. So we take the derivative of x, 1, plus the derivative of tan of x cubed. Well, that's going to take a little chain rule. So we're now taking the derivative of the tan of x, 20 tan of x cubed. So power is 3 tan of x squared times the derivative of the inside. Well, the inside is tan x. Its derivative is secant squared x. So we took the derivative out of the outer function, 4 all that cubed. But for the derivative of the inside, since it was a sum, we took the sum of the derivatives. The derivative of x was just 1. And the derivative of tan x cubed is 3 tan x squared times secant squared x. We had to use the chain rule for that part. Example E. We have to find the derivative once again. And this time, we're not starting out with the chain rule because this is a product. So we have to use the product rule. Product rule, if you recall, you have the first factor and then you have the second factor. And we take first times derivative of the second. Well, that's going to take the chain rule. Take the derivative of the second, we'll take the 3, sorry about my smartboard, leave the inside alone. Right. So we have first times derivative of the second. Oh, we're not finished though. We took the derivative of the outer function, 3x cubed plus 1 squared, times the derivative of the inside. So far, we have first times derivative of the second. We had to use chain rule to get that because it was a composition of function. Plus the second x cubed plus 1 cubed times the derivative of the first. So like that. Plus the second times the derivative of the first. That's it. Some of you want to do something with this. I mean, you could always factor out these two terms do have in common an x cubed plus 1 squared and an x, which could be factored out of both terms. But for now, we'll leave that. In F, we're given y equals u cubed, u equals x squared plus 3x minus 1, and we want to find dy dx. Well, one thing people think about doing, oh boy, let me just try to recalibrate this again. That's a calculus fairy. Okay, so one thing we could do is try to just substitute in. Since y equals u cubed, and we know what u equals, we can just put that in for u. So u, we could substitute in x squared plus 3x minus 1. Now we can find dy dx. So chain rule, right? Because it's not just x cubed, it's some function of x cubed. Derivative of the outer function, so we bring down the 3, leave the inside alone, and subtract 1 from the exponent. Now we have to multiply this by the derivative of the inside function. The derivative of the inside function, x squared plus 3x minus 1, is 2x plus 3. So that would be a nice straightforward way to get the derivative. Just substitute and then go ahead and get dy dx. I want to show you a less than straightforward way, and I really just, I'm hoping that what you're going to get out of this is that you can get rates by multiplying other rates. You can get derivatives by multiplying other derivatives. So bear with me for a second. We're going to do the same problem the second way. We were told that y equals u cubed. So if I find it's y equals u cubed, not y equals x cubed. So if I find the derivative, it's not dy dx. I'll find the derivative dy du, which equals 3u squared. And the other equation that they gave us was u equals x squared plus 3x minus 1. So if I find the derivative of this equation, it's not y equals, it's u equals. The derivative will not be dy dx, it'll be du dx equals 2x plus 3. So from the two equations, separately, we can find the derivative dy du and du dx. Well, derivatives are going to work like fractions. So if I want to find dy dx, I can actually multiply dy du by du dx. And when you multiply with fractions, you can cancel. So another way we could have found dy dx is to take dy du, and we have that here. That was 3u squared, and multiply that by du dx. And if you compare that to what we got for dy dx before when we substituted first, you'll see once we substitute in for u, we're going to get the same thing. We'll get dy dx equals 3. U is x squared plus 3x minus 1 times 2x plus 3. Same answer we got for dy dx by multiplying the derivatives, as we did by just substituting first and getting the derivative. So that's just something I want you to be aware of, that you can multiply derivatives to come up with another derivative. The last example we're going to do today is some crazy expression. The kids wanted to do this one. I wanted to do an easy one, but the kids wanted to do this one. So we have to rewrite it first. I really hope the smartboard allows me to write this. Let's see. That cosecant of the cube root, that's cosecant. Cube root means to the 1/3 power, right? And there's a tan of 2x in there. Now, remember the rule I have about setting yourself up for success. You need to have parentheses around each angle. Well, the angle for tan is 2x. But that's not a product in the numerator. That's the cosecant of all that. So we need another set of parentheses. We need parentheses around the argument for cosecant, around the angle for cosecant. Now we can take the derivative. Now this is going to be a quotient rule we're going to use because it's the derivative of a quotient. It's going to be way too long to fit on one line, maybe not even on 2 lines. I might need 3 lines just for the numerator. So to find the derivative, you start low. So it's low sine of x squared d high. Well, this is going to be a big old chain rule. For d high, we have to use the chain rule. The outermost function is cosecant. The derivative of the cosecant of an angle is negative cosecant the angle, cotan the angle. So negative cosecant, I'm going to leave the angle alone. It's going to stay the same. Cotan of the angle. So we fill in what that angle was. That angle was the cube root of tan of 2x. I can write it as tan of 2x to the third. I think because my smartboard's acting up, I'm going to write it as the cube root of tan of 2x. You're leaving the inside alone. You're just not touching it. Okay, so far, taking the derivative of the cosecant. Let's see where we are. So we started low. That was nice. And we're just beginning the high. We are a long way off because we just took one layer, the derivative of one layer. Okay, so we took the derivative of cosecant. The next, working our way in, the next function is to the 1/3. So to take the derivative of something to the third, it's 1/3, keep the inside alone, the same, to the negative 2/3. The tan of 2x stays inside. So we've taken the derivative of that layer. We're still multiplying, we're still taking d high, right? This is still going. We have to multiply it by the derivative of the next function, which would be the tan. So I got to go into the next line already. So times the derivative of tan of 2x would be secant squared of 2x. So we got that one done. And now finally the innermost layer, 2x, its derivative would be 2. So all of this is part of d high. So we have low d high less high, no secant. I think I'll write it the original way. It takes less room. Cube root of tan of 2x. So less high. D low. Oh, another little chain rule. It's a composition of functions. The derivative of sine of x squared is going to be cosine of x squared times the derivative of the inside. The derivative of x squared is 2x. That's our d low. So far we have low d high, big old chain rule. Less high d low, smaller chain rule. All over the denominator squared. That was a good tie. Okay, finally, I'm just going to skip over to the summary. When do we apply the chain rule? When you want to differentiate, when you want to find the derivative of a composition of functions. So to differentiate, that means find the derivative, a composition of functions. If you want to find the derivative of f of g of x, take the derivative of the outer function. The outer function's f. So it's f prime. Evaluate at the inside function. You leave the inside alone. So f prime of g of x times the derivative of the inside function. So times g prime of x. And finally, if you want to, you can multiply derivatives, come up with other derivatives. So if you want to get dy dx and you have dy du, what derivative could you multiply it by to get dy dx? Well, you'd have to have a du up here, so we'd cancel that du down there over dx. So dy dx equals dy du times du dx. Thanks. And I think that's it for today.